So what is alternating current, where we often write AC? Now you have run into direct current, which is the flow of current, which is just electricity, or you can think about electrons, which are flowing just in one direction. So if you kind of think back, so I have here kind of a simulation where you have a battery and it's hooked up. So I'm using PHET. I'll put up the link to all of these in the description below, so you can maybe build out these little labs for yourself. And you can see here that you have basically a battery which is hooked up. You have a light bulb, okay, which is constantly on because of the fact that you have a direct current. It is constantly flowing. You can see those electrons which are moving. So that means our conventional actual current is going to be flowing in the opposite direction. But I wanted you to see the actual electrons moving so that you can see that we have a direct current. So now, how do you switch over to an alternating current? And what exactly does this alternating current mean? Well, so in a quick kind of another simulation, okay, which I've created on the other side. So this one looks a little bit more complicated, but it's exactly the same, except instead of an actual battery, we have alternating current. And I just want to explain to you what this alternating current is. So if I turn this on, okay, and I let it run, okay, so you'll notice that you have electrons, okay, which are now flowing, but they're flowing back and forth. So this does not happen in a battery, because a battery will actually discharge. So it will go from one to another, okay, side, and the actual electrons are going to flow in one direction. So we call that just DC current or direct current. In here, the current is alternating. And what that means is that the voltage is actually changing. So the potential is changing to allow and to push these electrons in one direction. And then slowly it changes back and pushes the electrons in the opposite direction. So within here, you can see this light bulb, which kind of turns on and off. Now you might say, well, I don't see that happening. Well, that's because the frequency of this back and forth is so fast that our eyes can't really see it. Now, it's not that super fast, because in our regular outlets, at least in North America, we have it at 60 hertz, which just means, okay, that it's going back and forth 60 times. So you have 60 cycles, okay, so for every second that passes by. So now, within this alternating current, it will be nothing else but a periodic change of your electrons, which are flowing back and forth. So you see there that it's also being measured, and you can see that it creates this nice kind of a sine wave, okay, as you're going along. And if you're getting introduced to this, it's always super cool to be able to see this, okay, as you're moving along. So within here, let me just pause this, okay, and kind of take a step through. So you can see there that I'm also measuring the current. So this looks like the current is kind of at its biggest peak. Remember that current is nothing else but charge per second, right? So it's how quickly these electrons are moving by. So within here, so if it's reading out right now 9.88 amps, okay, so that amp, okay, is the amount of charge, so coulombs, okay, per every single second that passes by. And now, as you're going through, your actual power source is going to be changing. So as you're seeing this, so now it peaks, and now it starts to slowly go back, okay, in the opposite direction. Now it's positive, okay, and now it's falling. So notice that when you're looking at the M-meter, so the actual oscilloscope, okay, that is on the screen where the sine wave is captured, so it's going back and forth, so it's, you know, going in, and as it is reduced, right, the voltage also actually changes in the power source, so it's much less, and the actual brightness of this light bulb decreases, and the actual electrons are moving much, much slower now, okay, until the point where they basically stop moving, and then it switches back direction. So this is the alternating current. So it switches directions. So it alternates the current. So alternates the flow of the current in one direction. So as you can see there, now they're moving, okay, as you're going through, you can look at the light bulb. So it's picking up, and then now, okay, it is moving, they're moving to the right, and now it's going to take a peak, okay, and now it's going to switch back over, okay? So as they're going to the right and to the left, back and forth, back and forth. So as you can see there, so there you go. So they're moving to the left and now they're moving to the right. And at every single instant as it passes through the filament of the light bulb, it actually, okay, loses some of its electrical energy and it gets changed into heat and light. And then it kind of falls through, okay, carries forward, and then the voltage, okay, that you have within there, so that potential re-energizes it and then it goes back in. So that is what alternating current actually is. So that's what we have. Now, where does it exactly come from? Like, how can we generate? So, you know, we said there is a power source, and that power source switches the voltages back and forth and switches the currents. Well, if you think back of alternating current, it is to the understanding, so within here, so as you can see there, we have a coil and we have a magnet, and this might remind you of the electromagnetic induction. So when you are changing the magnetic field, you can, okay, induce an actual current which is going to flow. And that magnetic field, so I have a permanent magnet here, but it doesn't have to be a permanent magnet. Then we can figure out that the direction of the flow of the actual electrons in, okay, in this case it would be a solenoid. So if I would take this and you start using the Faraday's experiment, so in terms of understanding that there is an induced current by a changing magnetic field, so that's one, okay, thing that you have to know. And then you have to know the directions, which would be Lenz's law, okay, who has figured out which direction the actual current is going to flow. Now this is the conventional current, so that means the electrons are flowing in the opposite way. So within here, what did that entail? Well, so if you think of Lenz's law, and I'll put up a link up above there, I'm assuming that you do understand, okay, what happens. So if I would move this, okay, coil in, you know that the actual movement changes the magnetic field. So as this is going in, so our conventional current, okay, that we would have is going to, so you can use the right-hand rule, as you can see there on the screen, so it would create a north pole, okay, within, and then therefore the current, okay, would have been flowing downwards as I am moving this in one direction. But now what happens is, if you now take this, and of course, once you stop, there is no current flow. So this would have to constantly go in and out. Now, as it's coming in, okay, the current is flowing in one direction. But as you're moving this out, the current is going to start flowing in the opposite direction. So if you're moving this back and forth, you're going to create a current which is going to flow back and forth, and therefore creating an alternating current, as you saw there with the electrons, okay, throughout. Now, of course, this is not necessarily the way that we would design an actual where we're moving it back and forth, but something has to be moving around so that you are creating this change of the current, okay, going back and forth, back and forth. And that's exactly what AC currents are. Now, what's really neat is that in AC currents, okay, so just like in DC currents, so if you're building out a circuit, everything holds that you have learned before. So meaning Ohm's law is going to hold. So if you want to find out resistances, okay, and map it into between currents and voltages, it all still holds, just like in DC currents, and all your other rules will also hold. So meaning you can use Kirchhoff's laws, okay, and etc. in order to find out what's happening overall in these circuits. So there you have it. You had a simulation. Now you know what an alternating current is. It goes back and forth, and you probably will have now a lot of questions. How in the world are we utilizing this for the various applications, okay, that we have in our houses? Well, that's something for you to try to think about. Okay, for this video, that is it. We'll see you in a future one. Bye, everybody.